let's begin. So I just want to recap. We're going to work through this integral in the context of a normal distribution. So this is going to be a normal density, with this being in that variance. So that's just a normal density. If I were marginalizing something, this is the joint distribution of all these things. So let me just write this out just a little bit more clearly. This is the joint distribution. I don't know if I should use pi or f right here, because I kind of named them different things. I kind of like pi for posteriors, and I like f's for my sampling densities. But now I'm going to have a joint of both of them. And I can combine these things right here because I'm conditioning on the same stuff. So this is IID. So if I know what the parameters are, conditioning on other data doesn't help you. So I already know what the distribution of the data is, and I don't need that data to learn the parameters because I already know them. So if you know what these parameters are, you know with certainty, you have uncertainty just coming out of that distribution. And last time we alluded to, we have this extra source of uncertainty in mu. We don't know what it is, so we're going to average over it. What are we going to average this distribution over? Average it over our posterior. Our best guess is in what mu is. Just take this weighted average. So a predictive distribution, or more appropriately, a posterior predictive distribution is just an averaging of the sample distribution. That's one way to think about it. But again, what I was saying last time was, if you just told me this, I don't need to know any context of anything. If you wrote this down with that x there, I'd go, oh, I know what that is. Just updating this to a random variable. And so I'm going to use pi f, because I can't think of anything better to denote this sampling density. And this is x tilde mu given x in sigma squared. d mu, that's marginalization. So if you want this distribution, there's only one way to get it. So we didn't need to know anything about days to do that. We just needed to know about our probability class. And then we needed to make a connection that, because of IID-ness, I can just draw that. So if this wasn't an IID distribution and there was some dependence right here, you would have to model the dependency. So like in an AR model or something like that, an autoregressive model, I'd have to condition on the previous data. So that's what that would be. So those of you that ask me, what about not in the IID case? I would say, well, I'd use the conditionally independent distribution right there. And plug that thing in, and that distribution would have information about the dependent structure. So same exact process, no matter if you have an IID distribution or a non-IID distribution. You just have to model the dependence. And later on, I'll show you an example like that. We'll do a time series example. And I'll say this is just like the thing we did before. So I just need to condition a little bit differently. Anyway, in general, we just write it down like this. This is your original sampling distribution. The random variable is x tilde, and I'm going to integrate over the theta. So I'm going to update that to random variable. This is going to be the joint distribution. I could plug the cap x in here, but it's all IID stuff. So in the IID case, there is no conditioning. There is no dependence on the other data. So it just falls away, and this is just an averaging. Again, so I like thinking about this. I used to like to think about just IID-ness and think that whatever they're telling me is not right. They say that the data is IID. No, data given the parameters, knowledge of the parameters, that's what's IID. So the data is conditionally independent given all the modeling parameters, given that you know everything about the parameters. Otherwise, you can use the data to learn those parameters, and it kind of fuses the data together. We'll look at that maybe next week. We'll do some lighter lectures, some conceptual stuff, and we'll see exactly what I'm talking about. But we want to work through this calculation where that's a normal, this is going to be a normal. This normal is the posterior distribution, normal x bar sigma squared over n. And so it's a normal, but it has a different mean in the different variables. We worked that out. You worked that out. So I presuppose that the prior that I used right here was flat for this example. So if I gave you that posterior distribution, you would know right away it was probably Okay, we were using these formulas. I just wanted to kind of recycle these formulas and show you how to do this problem the easy way, and then we're going to go through it the hard way. So if I were able to establish that whatever this integral was, that it formed an e to the minus quadratic term, I would know it's normal. And I would instantly pivot and say all I have to do is find the expectation of the variance. This is a hierarchical representation. I can think of this different. I first collect a mu, I plug it in here, and then I collect out an x tilde. So that's joint sampling in a sequential manner. I could take both, the x tilde and the mu, all at once out of that distribution, or I could just look at this and say I'm going to sample mu, plug it in here, and then sample x tilde. And that's what's going on. And then I throw away the mu. That's integration. So that's weighted average. If you don't understand that, you didn't understand the Riemann square thing. So, you know, where you're uniformly weighting everything in Riemann squares, and then you use the height of the distribution. So this is the same thing, except the frequency of how often these mu's are proportional to that height of the distribution. If you set up a Monte Carlo algorithm, you can do this. So in general, I'll say this is the IID case, but if I did have dependence, as long as that sampling distribution here had that dependence being modeled, I could use the same idea. We'll see that more explicitly in a future homework. So I could just do this. T goes from 1 to cap T. I'll say mu comes from its distribution. X sigma squared, index on there, and then I'm going to get the x tilde. I'm going to get it from its distribution, but I'm going to condition on mu t here. That's that value is getting plugged in. Sigma squared, and I can condition on x, but it doesn't mean anything because it's all IID. And this is going to result these samples. So I'm going to have mu and x tilde, t, huge vector of these. T goes from 1 to cap T, the index. So this is just a collection. So I've got those joint samples. And if I want just the samples for that margin right here, just ignore that column. If I want their joint representation, I need both of them, and I can do things like correlating them and seeing what the relationship between them are. They're certainly related. If I wanted just the posterior inferences, we'd stop looking at that. That's integration. So that's super cool. That's my favorite thing about Monte Carlo. How easy it makes a problem so long I have a machine that can iterate over something really fast. And that used to be a big hassle. Now it's not. I feel bad for you guys that you'll never appreciate that.
The x tilde t is for the result, is that an x tilde t?
Yeah, it is.
Yeah, but yeah, sorry. Is it t1? I can't see it.
That's a T with a brace around it.
What are you saying with the t with the brace around it?
It's just an argument. I'm just putting it in parentheses.
Oh, you're just saying it.
Yeah. How about this?
I will
Watch this.
Just checking.
Smile. Smile. Now I gotta be a little bit more clear and put smiley down here. So arbitrarily I can switch all those things, which is done here. So, good question. So it's just a collection of all the elements. So we can use these formulas to just figure out the mean of this distribution. In a moment, we'll figure out this thing really is normal. We'll do all the integral. So I'm going to recycle these formulas. If I want to know what these expressions are, they're the distributions that are showing up here. Conditional distribution and marginal distribution. And so I'm just going to figure out what x tilde is. My formula is a little different because I'm also going to be conditioning on x in sigma squared. So for every operator that I see, I get to know that information. And I'm going to fill that in using the right notation. This is this. Double expectation. X tilde given mu. That's my theta in that other in general description, and I'm going to condition on x in sigma squared. And then I'm going to condition this expectation on x in sigma squared as well. Just to be clear, what is this expectation right here? It's the conditional of x tilde given all of that stuff. So it's built into the notation. What is this one over? This one's over mu. How do I know this is going to be a function of mu? It's going to be a function of all that stuff. Again, this is all IID stuff, so I don't need to know that. That drops out. It's not a coincidence that all the same stuff I do upstairs in the integral, I'm doing the same thing here. They're the same distributions. So this is going to be the expectation, x tilde, given knowledge of mu in sigma squared, the expected value of x tilde is mu. So that's just mu given x in sigma squared, and that's the posterior expectation. That's the expectation of this region right here. Again, these formulas aren't coming out of nowhere. They're coming from that integral. So this is x bar. So bang, what we thought. If I were going to predict what I think the next x is going to be, x bar is intuitively a good answer. You know, you might think there's other meanings, but it's because of the square function in the normal distribution, it makes x bar optimal. You can't beat it. You can do the same thing with this formula, variance. Work through it. Do it up here. So the variance of x tilde given x sigma squared, posterior predicted variance, is just the sum of these two things. It's an expectation and a variance added to a variance of an expectation. And I always recycle the order of these things every time I do it. The nice thing is it's an expectation of variance and a variance of an expectation. You add them together, so that's easy to remember. X tilde, I'm going to condition on that parameter that I'm integrating out. X sigma squared. Conditional on x sigma squared plus the variance of the expectation. X tilde given mu x sigma squared. Try to remember to condition, and the reason I'm always like, you got to condition on everything and you got to write it down, is because I'm just like everybody else. I might forget what that is representing, right? Forget what it means. So sometimes people shorthand their notation and it gets confusing. So this is this expectation, variance of x tilde. I don't need to know that or that because of the IID-ness, so I can cancel that out. Variance of the x tilde given knowledge of mu and sigma squared, well, that's just going to be the variance. So, and then I'm going to write this down, given x and sigma squared, plus the variance, that's this term. And I've got x tilde given mu, all that stuff. This was this expectation. So you always use that twice. So we already know what that answer is. That's mu given x in sigma squared. This is why I like this notation right here. If I forgot to write that in, I might interpret that as a posterior. And go, oh, I need the posterior distribution of sigma squared given x. That's an inverse gamma. I'm going to flip it upside down and work backwards. And then I'll flip it back upside down again and do a transformation maybe. But wait a minute. I get to know sigma squared. This isn't helping me tell the expectation. Given that, that's a constant. And that thing is just sigma squared. Plus variance of mu, given that we've already worked over the posterior variance. This is the posterior distribution. This is sigma squared over n. That's sigma squared, 1 plus 1/4. So boom. So that extra source of uncertainty, and I like this answer because as n gets bigger and bigger, there becomes only one source of uncertainty. We're learning that mu and we're learning it very, very well with more and more samples, so the inherent uncertainty attributed to mu is diminishing. That's the CLT Or if you want to think of it as the central limit theorem, you just get more out of the CLT. So super cool stuff. We already know the answer. If you took a regression class or something like that, you'd probably see something similar to that. Different derivation. Let's do the integral. So I want to do the full blown thing and work this out. Let me just remind you real quickly. I'm going to write this up on the board. I'm going to do the rest on the overhead projector. So what I'd like to do is do everything by hand on the overhead projector. You can see it. I'm going to hold you responsible for it. So on Monday, I'm going to photocopy whatever we write down. And I'm going to walk through it one more time, and I'm going to hand it out to all you guys. And then when we do this in high dimension, I'm going to go, it's that same thing as that handout that I handed you. And somebody's going to go, you handed me a handout? And then I'm going to say, go see Dylan. He's got some words for you. Dylan is paying attention right now. So we're all going to remind that person, yeah, there's a handout, and we'll give them a handout. That's what normally happens. I have versions where I do this on the chalkboard. It gets a little messy, so let's slow down and try to make this really neat, preserve our work, and give it to you guys. So I'll photocopy it this weekend. We'll walk through it one more time. Hopefully we don't make too many errors as we go, so I'm also afraid of it. Does anybody have a black sheet too with 0.07?
That's oddly specific.
You might see it better. These are 05s. This is the problem. That's not bad. It's a little.
Maybe you have a filler for exactly what we want, and then I can put it in this pen.
What are we waiting for? Alan is an engineer. Nicely done. Oh,
The new one. Is it working?
it's got it. Let's see, I got lots of weapons. Equal. Integral. How's that? Minus infinity to infinity. I'll probably drop those every once in a while and plug them back in. to the minus 1/2. This is x tilde's distribution, x tilde minus mu squared over sigma squared. So that's exactly f of x tilde given all the information, mu and sigma squared, times 1 over 2 pi square root sigma over root n e to the minus 1/2 mu minus x bar squared over sigma squared over n d mu. So that's that integral. And I can get rid of some terms. If I didn't know sigma squared, I would have to keep that around. And I'd probably have everything written down a little wrong anyway over here. So, but knowing sigma squared, I can get rid of that, I can get rid of that, and I can combine these two things. So I'm going to add together those two square terms in the exponent. So we're going to do what we typically do and write down after proportionality. And I'm going to start shucking normalizing constants, and I'm going to define this distribution up to proportionality, and then I'm going to recognize it, and it'll be a number. So this.
And this is the integral of that times pi integral we got on the board
Yeah.
now.
Yeah. This right here is f(x) tilde given mu in sigma squared. And this is f, or I'll say pi mu given x. So same process every single time. So it's kind of cool. Anytime you're doing a prediction as a Bayesian, this is what you do. And that might be one of the where Bayesians really caught on, is that we're integrating over all our sources of uncertainty that are modeled in the posterior. And it's got the right joint form. So you've noticed what's made Bayes popular, probably computational resources through the 90s made it feasible, and then forecasting, people are getting better forecasts because they're not assuming independence in anything. There's dependence if this was a joint posterior. All of that. And we'll see examples of that when we learn them, when we go to the part where we don't know sigma. We'll look at its joint distribution and integrating over that joint surface and not assuming independence is an important thing. So even in a normal example, when you don't know sigma, being a Bayesian has some advantages. They're small, but if n is not too huge, those advantages could be non-negligible. We'll get to that next week. E to the minus 1/2, so I've already gotten rid of both my normalizing constants. I'll just circle what I've gotten rid of. I've gotten rid of that. I've gotten rid of that. I'm going to combine these two terms into one big term. So this is going to be x tilde squared minus 2 mu x tilde plus mu squared. This is all over sigma squared. This is going to be plus, I should try to be consistent, but it doesn't matter much, mu squared minus 2 mu x bar plus x bar squared. And this is all over sigma squared over n. I've written this down under proportionality here. So there's constants in here that I can start chucking. So I need to think about mu. I can't throw anything away with mu on there. And I need to remember what the problem is asking at the end. I can't chop that stuff out. So let's just walk through this. Is this a constant term? I can factorize this term out and get rid of it. So we'll do that. Factorize, slide that thing out. We've seen that sort of thing a zillion times already, maybe 5 times, but eventually we'll see it a zillion. So we're going to get rid of that and write another under proportionality sign. Is that a constant? Can I get rid of that term? No. How come? We need mu. Yeah, can't. How about that one? No. No. How about that one? I can factorize it outside of the integral, but I can't throw it away. And the reason why is that the random variable that we're studying is that right there. So we can't get rid of the random variable of interest. So there's two things I need to pay attention to in this calculation. So very good. But I can get rid of that one, and then I can factorize this one out. I'm going to do that all in one step. So this is going to be proportional again, just because of this term right here, and everything else will be right. So I'm going to factorize this term out right here and put it outside, and try to remember that I can't shut it. So that's that term, and now I'm going to integrate between minus infinity and infinity. And I'm going to have e to the minus 1/2, and I'm going to have a bunch of other terms in here. There's two important things. There's the quadratic terms. There's the minus 2 linear terms. So let me just write those down. So this is mu squared, bless you. I'm going to collect my mu squared terms and combine them all in one. So I've got the sigma squared right there. And then I've got another mu squared term over here, and that's sigma squared over there. So this is going to be like that. Oops. Not inverse, that's too soon, right? I'm already into my algorithm. I know what the variance is, my brain just did that automatically, but I'm going to go slow. Just those two things, minus 2 mu. So I've got two of those terms. And here I'm going to combine those two terms. So it looks like I've got one here, x tilde over sigma squared minus x bar over sigma squared over n. Close that up. There's two terms, the two sources of uncertainties. Does this look familiar to you? This diagram? What does it remind you of? Yeah, plus. What was the example?
I'm asking that shouldn't it be plus in between the brackets, so we factorize the negative amount.
Oh, I see what you're saying. Yeah, these are added. Thank you. Yeah, I do that kind of stuff all the time. That's where I'm going to make a mistake. That's a great interruption. I never really understand. Something's helping me sometimes. What does this calculation look like? Just the integrate, the stuff inside. I've done this before in this class. Yeah, of which analysis? The mu, yeah, the prior was the full lone conjugate prior, not the improper version. But the conjugate analysis had that. Instead of using the prior, I'm using the posterior. And it kind of looks similar. The reason this looks similar is that the sampling distribution is also normal. So it's kind of a coincidence that that happens in this analysis. That won't happen for other analyses per se. It's just because the posterior and the prior were both normal in all cases. So it's self-conjugate or similar. So in self-conjugate cases, you recycle that calculation. That won't help you. It's just supports. So now I can recognize which normal this is, though. I can give it some terminology, and I can figure out what this integral is by doing this one step. And this is the part I want you to really focus on, and just remember it. And turn this into a reaction. When you see this integral, you know what to do. The integrand looks like a normal, and it's got an expectation, and it's got a variance. And I'm going to just throw some symbols on top of this. E and D. So just remind myself, these are really just the posterior quantities right here. So when I can identify what those terms are, so I can look at the variance term here, and I can instantly write down 1 over sigma squared plus n over sigma squared inverse. And I'm not going to simplify it any further than that. That is the variance. The expectation term, I look for the minus 2 linear term, and that's it. I take this term, the minus 2 linear term, and I multiply it by what I found upstairs. sigma squared over n. And I can write this as 1 plus n over sigma squared, if you will, and this is inverse. And I could probably simplify that. Maybe we should. So let's do that. Let's just take this an extra step. I'll write it like this: x tilde plus x bar. This is sigma squared over n. We're going to take that n upstairs eventually, but I'll just leave it there for a second. And this is going to look like it's divided by 1 plus n over sigma squared. So we can see these sigma squareds cancel each other. So this thing, we can come up with another name for it. I guess this is x tilde plus nx bar over, cut the n plus 1, whatever order. So it's just that thing. So keep track of that term. I'm going to have some cancellations in here. This is a box. I can remind myself of all that stuff. I want to back out just for a second. Lights, please. And I want to just remind us what a normal distribution looks like. So this is just an aside. So if I have a normal distribution, I think of the kernel as looking like this. So I'll just use Z. This is just an aside conversation about some normal distribution. I usually have my expectation. Oftentimes I call that mu, but I'll call it E for a second. Squared over V. And so if you show me this, I know which normal it is. I know the expectation of the variance. This looks like this. Z squared minus 2Z E 1 bar E plus B squared. And this is going to be over B. This is over B. This is over B. And so far, up until now, we've been ignoring this term. And we've just been focusing on those two terms. So, but we want to know what something looks like that looks like this. E to the minus 1/2 Z squared over B minus 2 Z over B dZ. Somebody help me out. What is this equal to?
E to the square root of to square root of
E squared over B. What about that? Positive 1/2. So we can flip it upside down. So let's be really clear about that. So plus 1/2 E squared over B. So, and then Dylan is correct. You also need the square root of the 2 pi, and I'll have the B in here, right here. If we didn't know the variance, we would need this term. Because we're not learning the variance, we're going to write something down proportional to this. Get rid of that. So what we need to know about is this, but later on when we're learning the variance, we need to remember that. So this is what I want you to remember. Helene's equation. You never forget this, because this is the equation that you learned during working. Call it that. Anybody else? You can't forget. This plus 1/2 e squared over b. I think we have that normalizing constant. If you forget about this part for today, no problem.
So are you saying you get that if you factor out the b squared divided by b? Is that how we did this equation?
I took this.
Yeah.
Okay, let me do this.
Yeah.
Let me do one more step. If I integrated this, dz, what is this? Not quite. It'd be the square root 2 pi b. If I had that over here downstairs, this would integrate to 1. It's a normal distribution. So that part I just factorized out and flipped it upside down. So if you can do that with the normalizing constant, pull it in and out, you can do that with that part too. That's where that comes from. There's a minus sign there. So that's why.
So you'll pull it out and you'll take the integral of that EV term, be able to remove it at time.
Factorizing out that term.
That makes sense. Okay.
So that's that. Exercising made us do over and over again probability. What's the normalizing constant? What's the normalizing constant? You're like, a new question. So I'm tired of this one. I can do it. But in Bayes, we do it all. So this integral right here is something we can write down. I don't want to forget this term either. I'll be specific about it and pull that down as well. So this one is going to be e to the minus 1/2 x tilde squared over sigma squared. And this integral right here is going to be proportional to, I could write down the normalizing constant if you want. I'm just going to do e to the plus, circle that because that always looks weird to me. And remind myself that is correct. And I'm going to have whatever these e's are right here. So I've already given myself some notation. So this is going to be e tilde squared over b. That's it. If you want, I could have multiplied by this. 2 pi b. This specific b right here, and this term would turn to an equal. So we're going to get rid of that, and over this. Proportional. But we'll remember that exists. That's a common mistake in a future problem. So now I just need to recognize this thing. Right now, I can already tell you this is normal. I could have told you way back here, this is going to be normal. So if I integrate over something like that, it's e to some quadratic term, so it's quadratic. I know that because I can complete the square real quickly in my mind. By the way, this is completion of the square backwards. Just don't want to get a completion of the square lecture. It's exactly that. So it's just completing the square. If you like completing the square and doing it the way we taught in high school, I did the exact same thing. So I just expanded the square and recognized what it was. I think that's what we taught in high school. So trying to tell me about formulas, memorize formulas, but I believe in memorizing processes. So this is a normal right here. So on the homework where it says work out the expectation and the variance, I just want you to recycle exactly the calculation on the board. I want you to get used to it. I promise you, I will test you on it in the future. Change the distribution and see if you can work with it. So, common trick in this class. Any Bayesian class you're using most hierarchical forms, iterative forms. So I already know this is normal, and I probably could stop doing everything and say, I'll just use the iterative form. So part of the testing game, I would stop it right away. I know what the answer is, I know how to get the answer, I know how to explain it to this professor. So I would do that. But since we're going through all the more details, let's finish the integral, we have to recognize which normal this is. I know it's something like that. So this looks like e to the minus 1/2 x tilde over sigma squared, and I already draw my square there, so I'll put it back. So again, real slow, so I don't drop all that stuff. This is e to the plus, I'll keep that circle because I never like looking at it. 1/2, at least that's there, and then I'll plug this thing in right here. That's my e, and I got my e. So I'm just going to plug those in. So x tilde plus n minus n x bar squared over n plus 1, that's also in the square sign, right there, divided by e. And I've got this thing right here, this is inverted, and I'm going to divide by the inverse. So I'm really going to multiply by this thing, right here. Is that right? So I can divide by this, inverted, or I can just 1 over sigma squared plus n over sigma squared. And that over sigma squared. So I've inverted twice. That's why the inverse sign is in. Got some nice cancellation in here. I need to do some expansions. And here, maybe I want to work on this term right here. Just chisel it down. This is going to look like x tilde squared plus, this is a little bit weird because that's a plus. Normally my hand would go straight to minus 1 there. So that's a plus, that's correct. 2x tilde nx bar plus nx bar squared over n plus 1 squared times n plus 1 over sigma squared. So that's cool, sigma squared just wound out in the right place. And I got some cancellation. Where did my blue tip go? My green. There it is. Right there. A little bit of cancellation, not too much all at once. And the reason I don't simplify everything all at once is because I want to be able to retrace my work. So I can know where everything comes from. So we're almost there. So now I just need to recognize this is a normal, and I'm going to do my same trick that we already did. I'm going to recognize the quadratic term and the -2 linear term, and I'm going to identify which normal that was. So we have to use that trick twice. So let me just rewrite this. One more time. This is e to the -1/2. I always kick that out in front. This is going to be x tilde squared, but there's 2 terms here for my x tilde. So I've got one of these n plus 1s right here, and I've got a sigma. So I've got this one, 1 over sigma squared, that's this here. And then I've got this other term. Let's just make sure I'm going to add, I think. Is this add? So I'm going to add this other term right in here. This term. There's this x tilde. We circle it. This one, we've already dealt with. That's here. Now I've got this x tilde. Ah, very good. So this is a subtract. Right here. So when the subtract is happening because of that plus, and I've got this leading -1/2 right in here. So I can turn that into a plus, so it's still a negative variable. So that one is a minus. I messed that step up all the time. So that would be a typical forward. So I'm just going to write this thing down. This is going to be x tilde. This is over one of these n plus 1s. Over sigma squared. We could recognize the variance by glancing at this. So now I've got the -2x tilde term, that's my random variable. And I've got only one term I need to fuss with here. It doesn't pop up here, so that's a little bit easier. So that's my -2 linear term. So I've got that term right here. This is a minus. So now I've got n x bar over n plus 1 sigma squared. Is that right? So that was just all this stuff. chunk that doesn't tell me anything about the random variable. So it's the stuff next to the random variable that matters. Now we're ready to go. So now this is my inverse variance right here. So I'm going to call this variance tilde star. And I'll give myself just a little bit of notation up here. We're going to show that this is a normal. It's got an expectation. I've already used tilde once, so I'll come up with something else distinguishing and call that a star. And this is going to be V tilde star. Right here. So my V tilde star that I'm after, I can recognize right there. So this is going to be equal to 1 over sigma squared minus 1 over n plus 1 sigma squared inverse. I panic a little bit because I see this minus sign and I think this better not be negative. If you give me a negative answer, you should recognize it. If you panic on the middle of an exam when you're doing something like this, tell me that I have an error in there, I don't know which minus sign I kicked around, I know this shouldn't be negative. So this can be simplified. So this is just n plus 1 down here, n plus 1 upstairs, so I just multiply by 1. 1 minus this 1 right here, I have a common denominator, so I can combine these terms. And this is going to be n over n plus 1 sigma squared. So just a little bit of algebra. Inverted. And I'll let you do the final step. This is sigma squared, 1 plus 1 over n, as promised. That's very cool. So the expectation is the last bit. I'm in cruise control. I know what the answer should be. So I'm just going to grab my minus 2 linear term stuff. It's right here. This is n x bar over n plus 1 sigma squared times this answer, sigma squared times 1 plus 1 over n. This stuff right here is the inverse. So I end up writing down at the end of this, my answer is x tilde given cap x and sigma squared is normally distributed with this particular mean and this particular variance. I am going to take this piece of paper. I'm going to go upstairs. I'm going to photocopy it. If you want it today, you can hang out with me. Otherwise, I'll bring it to you on Monday. That's it for now, you guys. So I am going to move to that confidence credibility question next time that I wanted to cover, and I just wasn't able to select it. So I thought we just needed to slow down a little bit. So we'll do some easier stuff, but I want you to digest this as well and know how to do it. So this is one of the things I guarantee I'm going to ask you to do eventually. So in a timely manner, so you know problems. Not too hard, but easy to get from. Sound good? Thanks, guys. Have a great weekend. Oh, you want it? I got you. Want to know Genie. Okay. And hold on to this. Come up and see me and we'll get it all taken care of. David. Caleb. Caleb. Jordan here. Can I say? That's right. Sure. This is when I remember your name. Slowly start process. You been? Excuse me, sorry. I got Ghazi. Widow. Sheng-Chen Li? Shang-Chen.
Yes.
Shang-Chen Li. Joseph. Caleb. The other Caleb in German.